Does it work? Yeah, okay. My name is Amira. I work as an Agile Java developer at Valtech in Paris, and there is a Valtech Sweden here nearby. I code in Java, and I code also in Scala. Despite coding, I'm a runner addict. So I started 2 years ago, and this year goal is to do my first marathon race in next April at Paris. So if you'd like to hear some tech news, you can follow me on Twitter, and you'll find all the code of this presentation on my GitHub account. I am also one of Duchess France leaders. Duchess France is an association aiming to promote female profile in the IT. So we help them to make them more visible and also to create a lot of vocation among girls and women too. So we are always looking for support among the technical community around the world. So follow us on Twitter to hear a lot of our news and have a look on our website. The Internet of Things. When I started doing my researches about the IoT, I was wondering when all this has started. And when doing my researches, I found an interesting report of Cisco. And the report shows the increasing number of population and in the meantime, the increasing number of connected devices. And according to this report, IoT was born between 2008 and 2009, when the number of connected devices exceeded the number of population on Earth. Today, we are around 7.2 billion people on Earth, and each one of you has at least 3 connected devices. And the most amazing thing that this number is increasing very incredibly for the next years, and we may reach 50 billion of connected devices in 2020. That's amazing. So imagine this network of connected devices with multiple technologies, from the wireless connection to the internet, to the embedded system with micro electromechanical system and so on. All these different systems connected to the network contribute to create what we call the Internet of Things. And these connected systems are capturing a huge amount of data. So, worldwide media users count into billions, and each one of these users are actually accumulating 10,000 of connection to content. So 20 terabytes of photos are uploaded to Facebook each month. And for example, for Google is processing around 1 petabyte every 72 minutes. So imagine exabytes, even many zettabytes of data are here now. And the most challenging things is how we can be analyzing all this huge amount of data. The data are, in the most of time, unstructured and in the meantime, text-based data. So there are some steps to follow to try to analyze the data. First, we have to extract the information from the data. Then, with the extracted information, we have to gain some knowledge, and we will use this knowledge to enlarge our wisdom. The vision of the future is that we'll have billions of machine and product from the physical and organical world that are going to merge to the digital world, allowing a near real-time connectivity and analysis. Imagine machine and products in the future will have the intelligence to help us deliver the right information to the right people with the right in any time and to any device. And when smart machines can communicate, they can help us, and other machines, of course, understand the problem and make a better decision, act fast, and save time and money. So we can improve product and services. But actually, we are a little bit far away to reach this level of consciousness. Matthias yesterday talked about the issue he had with some robots with wheels that he couldn't stop, at the end the robots burned. And the last year, I think, he bought the Now robots, and the Now couldn't connect to the network. They had some issues, so it couldn't work. So imagine this device with a lot of sensors on him, in spite of doing some keynote speech, give you order your favorite beer, for example, or even better, anticipate your need and order your favorite meal or launch your favorite music, and so on. So maybe soon we'll be able to do such things. But before going into the future, I wanted to share with you my IoT world and my connected devices. As I told you in the beginning, I'm a runner addict. So when I started running, I used a lot of devices. The first one was a phone application called Runkeepers. The Runkeeper helped me to measure my speed, to save my tracks, to know the distance, the elevation, the calories, and so on. But running with a phone, even using an armband, wasn't really easy for me. You have to hold it. Sometimes it fell off, and so on. I broke my phone 3 times. So I decided to change it, and the last year I started using a Garmin watch, more sophisticated device. And it's really, really efficient. With the Garmin watch, I am able to see my real-time speed as I'm running instantly, and also the device compute my rest time after activity. I also have the measurement of my heartbeats and a lot of other metrics. And the most funny thing is that I can synchronize all this data on my phone instantly to see all the metrics. And also I started using the little gadget, little thing, Withings, the Withings. And the Withings helps me to count my footsteps daily. As I am a developer, I stay a lot of time in front of my computer, not moving and so on. And this little device helps me to see if I had a healthy day or not. If I did the necessary step to say that I have a healthy day. So inspired from all these connected devices, I will try, the goal of today, will try to recognize the physical activity with a measurement coming from a little small sensor called accelerometers. So the goal of today is to try to recognize activity if we are jogging, walking, standing, or sitting. This kind of analysis can be used for example, by doctors to monitor the health status of people suffering from physical issues. The data we're going to use is coming from an accelerometer. It's a small sensor that we can find in all smartphones. And the accelerometers measure the acceleration. It's used also, for example, by the Google Maps to estimate your arrival at the destination when you do navigation to a destination. So it's based on the acceleration. That's why sometimes it shows you if you go by walking, you'll take 10 minutes, and then you walk faster, and then you see, I'll take 2 minutes instead of 10. It's based on the accelerometer and other sensors, of course. So each acceleration coming from these sensors give us 4 information. The first one is the timestamp, and we have the 3 forces according to the 3 axes, the x-axis, the y-axis, and the z-axis. The unit is meter per second, and the accelerometers is taking a lot of measurement during time. And all this successive measurement during a time interval are called time series. So, first step to do is to collect the data from our sensors. And to do this, I implemented a phone application listening to my sensor and then posting all the information through REST API to my server, where it's stored to my database. The code is available on my GitHub. You can find the REST API code there. So the application is pretty simple. I have a welcoming page where I can set my server URL. And then when you push the start button, you switch to another screen when you can start or stop listening to your sensor. And if each time you start listening to your sensor, you can see the refreshment of the measurement coming from your sensor. So here we saw how to get the measurement from our smartphone for our sensor, how to post it to a server. Now we are going to see how to store all the data. And to store the data, I used Cassandra. Who knows Cassandra? Yeah. Whoever used Cassandra? Oh, nice. So I'll do a quick reminder. Cassandra was created by Facebook. It's an open source project since 2008. The current version is 3.3, released yesterday. As now we're going to have monthly release for Cassandra. Cassandra, of course, is an NoSQL database, column-oriented, which tends towards distributed table abstraction type. Cassandra is scalable, it's really easy to use, we can have a lot of data center with Cassandra, so it helps us to have a continuous availability. And just to see the most important thing, how write is done on Cassandra. If you like to insert some instruction in some data on Cassandra, here I used the SQL, the Cassandra query language. For those who doesn't know Cassandra, you see it's pretty similar to SQL. Here I'd like to insert some users' information, the login, the name, the age. So what happens exactly? That we have to create an SS table on our disk containing our primary key, which is the login here, and 2 columns containing our value, and each columns will have an auto-generated timestamp. So if I'd like to update, for example, the age of my user here, what happens is exactly we are going to create a new SS table on our disk with the new information and a new timestamp for my age column. So what happens if I'm going to delete the age? Of course, we're going to have a third SS table with a column age and what we call a timestamp. It's a marker to say that the value does not exist anymore. So what happens if we'd like to read the value? So in our case, all the SS table, we get all the 3 SS tables from the disk, we read all the SS table, and then we keep only the value, the column containing the latest timestamp value. So here we are looking for the age. So in our case, the value will be the null one, the removed one, because it's containing the latest timestamp. So, well, here, when we write, when we update, when we delete in Cassandra, we create a new SS table. So I know you already don't know, maybe. The limitation of a Cassandra row, it's about 2 billion of columns. So if each modification we're going to create a column, sometimes we may possibly reach the limitation. Of course not, because in Cassandra there is some automatic mechanism that allow us to do what we call the compaction. So the compaction occurs automatically, and what is going to be done, it's a new SS table that is created, and we are going to copy the latest columns value, so the columns containing the latest timestamp, to this new SS table, and after all, we're going to remove all the 3 SS tables. That's nice, but remember, I'd like to store my time series data. So if the compaction occurs while I'm going to store all my time series data, I lose most of my data. So thereby, we're going to use another model and not the classic Cassandra model. Here we're going to use the historical model. So the first step is to identify the information that we're going to keep. In my case, I'm going to keep the user ID and the timestamp. So for each user ID, at each instant, I will have some information. And so I can store a lot of data as needed. My model will be like this. I have my accelerometer table containing my user ID, my timestamp, the 3 forces through the 3 axes. And so I have my partition key containing the user ID and my clustering column containing the timestamp. Let's have a look to the logical view. So for each user, for each timestamp, I'll have my different value, my different acceleration, and so on. And if we have a look on the disk, I'll have my row containing my user ID, and I have my timestamp here with the different values. So here we are sure if the compaction occurs, we're not going to lose our columns, as each column has different values. And what the problem here, as we are going to store historical data, is that we may reach this limitation too, because we're going to have a lot of columns, and if we store the data, acceleration data for 2 months, for example, for 1 month, not even 2, we are going to reach the 2 billion of columns. So one solution is to add another information so we can store more data. And in my case here, I added the date. So I'll store the acceleration daily. I'll have a row per day. And here I'll have a compound key containing the user and the date, and my clustering column will stay the timestamp. So in my logical view, I'll have for each user and each day my timestamp and the different value. And if we have a look on a disk, I'll have my row with a different measurement for this day, and the next day I'll have the other values, etc., etc. So that's pretty fine. And if I'd like to query my data, I can't get all the data at once. We have to do some range queries. So here we have to specify the timestamp range to get the data measurement at this time interval. And also, as we're going to store the acceleration, maybe we need to get the latest acceleration before. So for this, I added a clustering order. We can add a clustering order to get the latest acceleration before. Here I choose a descent order, so I'll get the latest measurement before the older one. Another way to do the storage for our acceleration, we can use the TTL, the time to leave. Actually, maybe I don't need to store it forever. I only needed to store it just for analysis and then remove the data from Cassandra. So in this case, I can use the TTL and tell Cassandra that this information will be stored a short time. Now we saw how to get the data from our smartphone, how to store it in Cassandra, and we're going to see how to analyze it. And to analyze the data, I choose Spark. Does anyone know Spark? Ever used Spark? Oh yeah, nice. I'll do a quick reminder for those who didn't know Spark. Spark is an open source project too, since 2010. The current version is 2.5. It's all written in Scala. And Spark is a big data processing framework built around speed, ease of use, and sophisticated analytics, of course. The main part of Spark is the Spark core. It provides an in-memory computing in-memory computing capabilities to deliver speed. And the Spark core can also offer support for a variety of languages like Python, Java, Scala, and R. And despite the Spark core, we have a lot of additional libraries, like the Spark SQL, Spark streaming we'll see it later, Spark MLlib around machine learning, and the Spark graphics. So Spark works with a lot of data sources. There are some data sources that are pre-packaged with Spark, like Hive, HDFS, and so on. But Spark also provides a point of integration for other type of data sources, like for Cassandra. And Spark works with a specific notion, which is the RDD. The RDD, the resilient distribution data set. It's a collection of objects that can be stored even in memory or on a disk across a cluster. They can be operated in parallel, so they are fault tolerant. And what we do in Spark with the RDD, so we have our input data exposed as an RDD, we do a lot of transformation analysis, and then we apply an action to get our final result. And just to get you, for those who doesn't know Spark, I added a small, simple, the most famous one around Spark. It's word count. Here what we'd like to do is to count the word occurrence in a file, text file, and keep only words that occurs more than 3 times. So the first step is to create our Spark context. Here I specify the app name, where it go in the cluster manager, local, standalone, and then I start my Java Spark context. And the next step is doing all the transformation on my RDD. The first one, I'm going to read my file, to split it using the space as a separator to get all the words. So I'll have the RDD of words here. And after all, I'm going to apply some transformation on my RDD of words. First step is to create a tuple. So for each word, I'm going to create a tuple for having the word as key and the value 1. And after all, I'll apply another transformation here, the reduce by key, to reduce them. So I'm going to use the key, which is the word, to do the sum of the values. Then I'll have, as a result, tuples with the word and the total of occurrence in the file. And the last transformation is to filter them. So I have to keep only words that occurs more than 3 times. And the final step is the action I do here. So I collect result to show it or whatever to do with the result. It's pretty easier, and Spark works as a set of independent processes on clusters, coordinated, of course, by the Spark context. What Spark context can connect to a different type of cluster manager, even in a standalone mode, local, or using Yarn or Mesos. And then the cluster manager will allocate the necessary resources and acquire executors to run our computation that we defined in our application code. So Spark is really fast, flexible, and very, very easy to use. You can start using Spark very quickly. We saw how to do all analysis, how we can do some analysis with Spark, but the interesting part is to do it in real time. So to do our analysis in real time, we have to connect Cassandra to Spark. And to connect Cassandra to Spark, I used an open source project, which is the Spark Cassandra connector created by DataStax. It's an open source project, all written in Scala, and it helps us load the information from Cassandra to Spark and write the result from Spark to Cassandra. So what actually the connector does is to expose the Cassandra tables as RDD to Spark. If we have a look to the Spark context, we don't have a lot of difference. We only have to add 2 information around Cassandra, in the URL and the port here. So, and if we'd like to get all the data from Cassandra, there is already a class defined in our connector, which is the Java functions here that takes the Spark context, and we can query our table. Here it's my key space name, which is activity recognition, and my table it's called training. And after getting my RDD of rows from my table training, I can do my queries on it, so I can extract the information I needed. So here we saw how to connect Cassandra to Spark, but to do it in real time, we're going to use Spark streaming. And what the Spark streaming does is to listening to stream data, slice it into batches of data, and each batch of data will be computed in the Spark engine when we have a batches of result at the end. And so we're not going to initiate a Java Spark context, but a Java streaming context instead. And the difference between the 2 contexts is just here with these parameters. We add the parameters to define the frequency of the streaming. Here I said each 2 seconds you're going to stream the data from Cassandra, do the analysis, and give me the result. After initializing my Spark Java streaming context, here I have to listen to my receiver. The receiver is going to get all the data from Cassandra. There is no native implementation for a Cassandra receiver in Spark streaming, so you have to do your own receiver. I'll show you later in the next slide. So here I listen to my Cassandra receiver, I give him my Spark context and so on, and then after defining my receiver, here we have to do all the analytics we have to do with our data, and after all, we have to start our streaming context. So we listen to the receiver, we tell him what to do with this data, and after all, we told him to start. And here I told him to wait for my termination condition. And my receiver is pretty easy to implement. I have only to extend the receiver class. I tell him the type of return and to override 2 methods, the start receiver methods and the stop one. So now we saw how to store the data from the accelerometer to Cassandra, how to stream it in real time with Spark streaming, how to do the computation in the meantime. And the most important part about the computation is the prediction. So the goal of today, of course, is to try to recognize physical activity. We have measurement, we have a lot of data, we store it, we stream it, okay, but we're going to analyze it to get this information, to guess if we are walking, jogging, standing, or sitting. The measurements are coming from our accelerometers, our time series, so the problem here is a classification problem. We'd like to classify time series into a lot of classes, physical classes. So we're going to use machine learning. For our multi-class classification problem, the notion to note is that we are trying to label an unknown patterns using unknown patterns. And to do this solution, there are a lot of algorithms in machine learning. The first most used one is the logistic regression. The logistic regression works in a binary manner. Success, fail, win, lose, etc. Here we have to classify in 4 classes, so we can use the multinomial logistic regression algorithm to classify into multi-classes. Note that the logistic regression algorithm does not support independence between random variables. There are another algorithm, the naive Bayes classifiers, which is based on some hypotheses. For example, if you have a small object with a rounded shape and red color, you can say it's an apple. But the naive Bayes algorithm is outperformed by other algorithms like the random forest. And the random forest is based on a multitude of decision tree containing a lot of assumptions. And today, I'll present you the random forest algorithm. Well, I didn't do a benchmarking work to compare all the algorithms. I tried the random forest one, and I get a very pretty good accuracy. So I kept it. And the random forest is containing a lot of decision tree when you can have your computation, your features computed, and then using your features for prediction, he can tell you which activity are you doing. We are going to use the Spark ML library containing all the classes needed for this. And before showing you the code, you have to know that the random forest is a supervised learning. So first, you have to train your model, and then you give him some feature, and he will be able to predict the results. So to train my model, I have first to collect the data with already known activities. Then I have to identify features from this data. I have to compute the features identified. I have then to create and train my model, which is a random forest model. And after all, I can ask my model to predict the result. So I had a very difficult step in the beginning. And I want to do some special thanks to my friends and colleagues who helped me to collect labeled data. I make them run on the floor, at the office, to sit, to stand, to walk, etc., etc. So they helped me collect data for my training model. And the data collected, I stored in my training table, containing already my user ID, the activity, as the data is labeled, and the different information for the acceleration. Here I have my compound key containing the user ID and the activity. And to collect this data, I also implemented another option on my Android phone app to help me, not them too, to collect the data. So when you click on the collect data button, you switch to a new screen when you can tell your name, select an activity from a drop-down list, and then you push the start button. I added some delay before posting the data, just to help me cleaning the data afterward. So when you use your smartphone, you push the start button, you're not running instantly. So I added a 3-second delay before starting posting, so the people are already running, and then I have the correct data. And after getting all the data, it was stored in Cassandra. I have to analyze it. But before showing you the analyses, just to remind you, you saw my colleague. We were a few people, so I don't have a very, very big volume of data. I'm not treating very big data here today, but I'm showing you the tools to do it in the future if you have a very huge amount of data. The first step to do with my data, with my time series I stored, is to slice it. I have to slice it into time interval, to windows. And to do this, you have to check your data. For my case, for example, I slice it into 2 seconds. That's the streaming frequency too. And after slicing it, you can analyze it. Here, for example, you have a chart for a person who's sitting and this one for a person who's standing. And just by looking to the two charts, you can find the difference, guess the difference between the two. Here, the white chart is under the X and the Z one. And when you're standing, the white chart is above the two others. So I can say, if I compute the difference between this one and one of those, I can say if I'm standing or sitting, depending to the values if it's positive or negative. That's pretty easy. But this one is a little bit harder. Here I'm walking, and here I'm running. And if you look to the blue charts, you see when you're walking, the chart is really smooth, with the smooth peaks. And when you're running, here it became really tense, with a lot of peaks. Here, for example, you can look to the amplitude. You say when the amplitude is very big, you're walking. And when the amplitude is very small, you're running, actually. The amplitude have to be measured peak to peak, so we have to take the bottom, the top of the charts. But I also added a lot of other statistical measurements, like the average acceleration. Here the difference I show you, the variance, the standard deviation. I have the average absolute difference, the resultant, and the amplitude. Some of this measurement, I did it for each axis, so 3 times for the X, the Y, and Z axis. And to do all these measurements with MLlib, first I get my data from Cassandra, my RDD, then I have to transform it to a vector, because the statistical library in machine learning works a lot with vectors, like all the statistical libraries, of course, with R or 2 also. So here I call the multivariate statistical summary class, which contains already defined methods for computation. It contains the mean, the variance, and a lot of other statistical measurements. So I didn't implement anything. I only had to use the already existing methods in the library and to combine them to do all the computation I needed. And after doing all this computation, I had a vector containing the result of each interval of measurement. I created a vector of the result of features, and then I used these vectors to create what we call the label point. And the label point is the base of our decision tree. The decision tree had a collection of label points. And its label point contained the label, which is the activity, and our vector with the values according to this activity. So the next step after creating our label point is to create our model. So before showing you the random forest, I choose to show you the decision tree. So the decision tree had some parameters. Here I used the default parameters one. 20 here is among the lowest value of depth that we can use for decision tree. And then you have only to call the decision tree class and to train your classifier, giving him your training data and the different properties defined here. And to train my data, I have to split it into training data and test data. All the data I have measured with my colleagues are split into 60% for training and 40% for testing. The testing data helps me to compute the accuracy of my model. So after creating my model, I have to test the accuracy just to be sure that my model works fine. And then I print my accuracy to compare my model with the other ones. And I did the same for the forest tree. The only difference between the decision tree and the forest tree, it's here we have to specify the number of trees. I choose 10 to construct 10 trees. And then here here we have to also tell how many values we're trying to guess. I have 4 activities. Here I used my enumeration containing my activities to get the number of activity to guess. And after all these are default values too. I didn't really needed to specify some parameters with other values. The default one was sufficient for my case. And after all, I trained my classifier the same way with the training data, which are 60% from all data, and I printed my accuracy. And here the result. So I had around 40,000 training acceleration stored. I computed 15 features, and I have 69% accuracy for my decision tree, but for the random forest, I had the 92% of accuracy. You can see here my random forest is more precise than the decision tree model. And I'm going to show you how it works. So I have to share my screen first. Hello. Yep. Here we go. Yesterday I had some issues with the resolution of IntelliJ. I hope it works this time. Sorry. So the first part is my REST server. It's a very basic application written with a Spring Boot that starts a small server which is going to receive my posted acceleration here. I'm going to log it so you can see the logs, enter. And you see, oh no, not yet. Oops. Okay. And after all, I insert the data to Cassandra. Nothing complicated, nothing mystic on it. So I started. And I'd like to share my phone screen. Hope it works too. Okay, thank you. Lisa. Okay. Cool. Up. So here my app, where I already typed my URL for my server. And if I push the start button, here we go to the posting screen. And if I start listening to my sensor, so here you are seeing my sensor measurement updated in real time. And you can see the logs here that are stored in Cassandra. So, oops, I'm going to stop it. Up. And then I'll switch to my other part of project, which is Spark. And here I created a prediction service with my context here, with the connection to Cassandra, and I have my methods to do real-time streaming. Here I have my Java streaming contexts, my Cassandra receiver, and I'm going to start the prediction here. You can see the batches running under. And if I switch here, okay. And I'm going to show you also the results. I did a very, very basic HTML page to show the result. Here you're seeing the result of yesterday, because I'm not posting now. Sorry, you can see everything or not? No. Same issue as yesterday. Too small. Yep. Here we go. And I'll try to show you my phone. Start. Here. Start. So here he's seeing my phone as sitting activity. Because when I did my measurement for training, I was holding the phone like this for sitting, and like this for and the other orientation for standing. So I'm going to remove my phone. You're not going to see my screen, just to show you the other activities. Oops, sorry. Up. No, I'm going to do sitting activity just to be sure. No, I'm not walking. Sitting, okay. Now I'm standing. I'm not jogging. Hello? Yeah, standing. And if I start walking, I don't know if I can start walking on stage. I'll go under. Yes, I do some jogging, sorry. Yeah. So actually, I connected my phone to my local as a local network to my PC to get the data, posted data. Okay, I'll stop it. Stop. I'll stop here. Stop it. Yep. And I stop posting. Yep. Yeah, thank you. Here we go. So just to conclude, here I collected data from a device, I analyzed it. I used one sensor, and there are a lot of sensors in an Android phone or other smartphones. We have the gyroscope for the rotation, the temperature sensor, the pressure sensor, even the light sensor. So all these sensors can be combined, and we can do more sophisticated analysis. So here I showed you just one possibility, and you have a lot of possibility to do with such a device for yourself. Thank you. And if you have any questions, yes.
How so to speak, this accelerometer?
Yes.
When we're just scanning, it still gives fluctuations. Could you stand so still that it didn't?
So the answer, the question is that how we have a different variation of measurement with the accelerometer if I am standing or sitting. The sensor actually works in real time. I launch it with a specific frequency, and the measurement is done by the accelerometers, cannot be stopped and changes even if I'm standing or sitting. The only thing that you're worried about, I think, is the prediction of the activity. This is the error. I had 92% of accuracy, so I had 7.8% of error percentage on my application. And sometimes when I'm moving this, the analysis done is wrong, and it gives me the wrong activity associated to the movement.
But if it's standing on the table, if you just put it on the table, it will show.
Sitting, because I trained my model telling him that when the phone is in this position, the measurement taken by my sensor in this position are for sitting activity. That's all. If I told him sitting will be this, then the prediction will be sitting for this position. That's the training part. Yes, I saw a hand. No? No questions? Yeah.
In your example, you trained the model. How did you execute the model?
Oh, yeah. So the model after training, I save it. I save it into, I store it, and I'll show you the code. Here. No. I can't see everything on my screen. I do the shortcuts. Yep. After you see everything or not? Tick here. I trained my model. The question was how we use the model after training it to do the prediction. So after training my model here, I store it. And to do the prediction, I have to get my model, to give him the feature, and to tell him to predict my activity. And the prediction is pretty easy. So if we go take here, I had a lot of methods to do the prediction. Predict. So the more tense class. So here you can see all the features that are computed, stored in an array. And in my predict methods here, I get my model, stored model, and use the methods predict and give him the features computed for these actions. And then he gives me the analysis, the result, the label. That's all. Yes.
So it's a statistical model that is saved in a
Yes, yes. Yes, on my PC here. Yeah. Yep.
How will it be possible to apply a non-supervised learning algorithm to this problem?
I didn't.
Could you apply a non-supervised?
Yes, yesterday other one asked me at the meetup about how to use another unsupervised learning. Actually, it's the easiest way with a training model, but we can do a deep learning and use a mechanism to let the algorithm learn by himself and try to predict what we are doing. It's more difficult. Actually, it's done by some companies like Google or Facebook. It's a pretty high level of algorithm. I choose the simple one. And also, just to give another sample, this solution, not this the same, but inspired by the accelerometer sensor, is used by Spotify developer to suggest the music while running. In fact, when you're working for Spotify, no? And I found this very, very intelligent and very logical for me. I hear music when running, and using the accelerometer to find the tempo for music, it's pretty awesome. So yes, we can do more sophisticated solution to analyze the data, but it's a high-level algorithm, more difficult and not really having a good accuracy depending to what we try to predict.
The choice of the length of the window.
Yes.
Seconds, is it how crucial is that, and was based on some?
So the question was about the choice of the time interval for analysis. I chose 10 seconds according to the data I stored. When I saw the chart of the data I stored, the most important shape of my chart was interesting during 2 seconds. So that's why. But it's very, very personal. If you have another data, another time series with another shape, you can choose a larger interval or maybe smaller. I don't know. So yeah. The frequency of streaming. The question is about the frequency of streaming. Here I choose 2 seconds to stream each 2 seconds and to get the latest 400 entries to Cassandra. So you can find my code on my GitHub. If you have another questions, you can send me questions or even improve my code by pull request. Feel free. You'll find different details on the code with the different choice, etc. Any other questions? No, time is up. Yeah. So thank you everyone.